we went over today in class. And I took the SAT and the ACT this weekend, but on the
Hey, how'd you get a scholarship without getting the results back from your SAT?
well, yeah. So in back in September, I took the SAT a lot earlier than most juniors.
Okay.
Ended up getting like an 1170. You've seen the score on that. I got 11 to 70 on that. And then I took the ACT and I got a 26. So I could send those scores out pretty early to them, and they were able to.
Okay, I got it.
Mm-hmm.
Let me go to my chapter on polar coordinates and see if I can come up with some interesting problems.
But I actually just had one question about a problem that I saw on the SAT.
Okay.
Because we're going to be getting into it too. Our teacher told us that we'd be getting into it before the semester ended.
Okay.
So it was a problem over vectors, and I was completely lost on what a vector is and how to maybe go about just solving a simple vector problem.
A vector has magnitude and direction, as opposed to speed. Speed is the absolute value of a vector.
Okay.
Well, no, let me take that back. Not all vectors are velocity.
Uh-huh.
But all vectors have magnitude and direction. If somebody weighs 200 pounds, then they are exerting a force directly towards the center of the earth of 200 pounds.
Okay, yeah.
If somebody's pushing a box up an incline and they're pushing that way, they're exerting some force on that box, but the angle is in the direction of theta.
Okay.
In other words, at a certain angle. So vectors have two things going for them. Magnitude, which would be the weight of the person, or the force exerted on that box. Maybe I'm pushing with 100 pounds of force.
Okay.
But also velocities. An airplane flying in this direction has a certain speed, let's say 500 miles per hour, and it has a certain direction that it's going. So whenever you're talking velocity, you're talking vectors. And vectors also apply to forces, and I can't think of other stuff. But vectors are different from scalar quantities. Scalar quantities have one quantity only, like temperature. A temperature is a scalar quantity. It's not a vector. There's no direction involved with temperature. A measurement of a piece of wood is a scalar. No direction involved, just magnitude. Well, vectors have magnitude and direction.
Okay. So why are vector problems then put in brackets?
It's just a way of showing a vector. In other words, the vector might have that point right there. Well, I can figure out what the coordinates on that point are, right? In other words, the sine of theta equals y over 500.
Yeah.
And the cosine of theta equals x over 500. So again, y would be r sine of theta, and x would be r cosine of theta. And in this case, r would be 500.
Okay.
Okay? So the thing about vectors is that they can always be broken down into their x and y components. For example, let's say I've got this airplane flying at a 30-degree angle. Okay? Well, I could look at this and I could figure out that the x component of that vector is cosine of 30 degrees times 500, right?
Okay.
Because of this. X is r times the cosine of 30. And y is r times the sine of 30. Well, sine of 30 is 1/2. So that's 250. And this would be 500 times root 3 over 2. Would be the x coordinate. So what's that? 250 root 3 is the x coordinate. And I don't just mean the x coordinate. Let's talk about this. What I mean is that let me see the best way to explain this. Instead of velocity, let's talk force.
Okay.
We have 500 pounds of force at a 30-degree angle being applied. Okay?
Yeah.
That is the equivalent of applying 250 pounds of force directly vertical and 250 root 3 pounds of force in a horizontal direction.
Okay.
Say you had two people. One of them was pushing up at 250 pounds and the other one was pushing to the right at 250 times square root of 3. That would be exactly the same as a third person pushing at 500 pounds at a 30-degree angle. In other words, you can always break down vectors into their horizontal component and their vertical component. And the beauty of that is that then you can add vectors. Let's say we've got that plane flying at 500 miles an hour at a 30-degree angle from the horizontal, or the x-axis. What if we have a wind that's blowing at a 45-degree angle, a 50-mile-an-hour wind? That's MPH, that's MPH. Now, if you want to know what the airplane's going to do, clearly it's not going to go at a 30-degree angle, right? Because that wind is going to push it. It's going to affect the direction of it. Well, how do you solve where the airplane ends up going? Well, you break it down, first of all, into its x and y coordinates. We already figured out that the x coordinate was the cosine of 30 times 500. So it's 500 times root 3 over 2. That's its x speed in the horizontal direction. The vertical speed is 250 miles per hour because that was sine of 30 times 500.
Okay.
Now we're going to do the same thing to the wind. We're going to break it into its horizontal and its vertical speeds. And then we're going to merely add those to the airplane's horizontal and vertical speeds.
Okay.
Okay? Now, what is the wind's horizontal speed? In other words, what is its equivalent speed in a horizontal direction along the x-axis if it's going in this direction at a 45-degree angle?
Horizontal speed would be the cosine of root 2 over 2
Times 50.
times 50. Okay.
So you got to multiply it by r.
Okay.
Okay? And it's negative, right?
Yes.
Because it's going in a negative direction. Vectors have direction. Up is positive, to the right is positive, to the left is negative, down is negative.
Okay.
Okay? And then its vertical speed is positive, root 2 over 2 times 50. So there's its vertical speed. There's its horizontal speed. This is the wind. So we're going to take the wind's horizontal speed and subtract it from the plane's horizontal speed. So we got 500 root 3 over 2, and that wind is working against it by this amount. So that would be the net horizontal speed of the airplane.
Okay.
Now, what's the net vertical speed of the airplane? Well, we got 250 plus root 2 over 2 times 50. And it's plus because the wind is helping us in a vertical direction. It's going in the same vertical direction that our airplane is.
Yeah.
Up.
Okay.
Okay. And now that we have the vertical component, that's the speed the airplane's actually going relative to the ground. And this is the speed it's going horizontally relative to the ground. So now we can draw a new picture and figure out exactly where the airplane's going.
Okay.
The vertical speed is 250 plus that. There's our new vector. We know its horizontal speed, which is the magnitude. We know its vertical speed, which is that y measurement. In other words, the x measurement is this thing down here. That's a speed in the x direction. Its speed in the y direction is this y measurement, which is that. Now, if I want to figure out what this angle is, I use the inverse tan function. In other words, that angle is going to be the inverse tangent of y, 250 plus root 2 over 2 times 50, divided by the x, which is 500 root 3 over 2 minus root 2 over 2 times 50. And that will give you an angle. And that's how I figure out the new bearing of my airplane. In other words, my airplane is not going to fly at a 30-degree angle from the x-axis. It's going to fly at more like a 60-degree angle, because that wind is constantly pushing it up and to the left. But the basic premise of this vector problem is pretty much all vector problems follow this. And that is, you figure out the x and y component of the original vector, the x and y component of the wind, add those together, and you got a new net x and y speed. A really good problem for vectors is this problem right here. You got a soccer ball. You got somebody's tugging it with a 100-pound weight in that direction. Somebody else is tugging it with a 150-pound weight in that direction. What amount of force would a third person have to exert so that the ball did not move? Notice that without this third force, that ball's moving. If that guy's tugging it in that direction at 150 and this guy's tugging it in that direction at 100, there's a net vertical movement going to take place. The ball's not going to stay there. But if there's a third person down here tugging it at some angle and some X amount of force, the ball stays perfectly still. In other words, all three forces cancel one another. Well, how do you figure out what this force is and what the angle is? Well, by breaking this thing down, each one into its components. In other words, if that's at a 30-degree angle and that's at like a 60-degree angle, then you figure out the X and Y components, add them together, figure out what the X and Y component has to be of this third vector such that there's no motion. In other words, everything has to cancel out. I've got to cancel out the net vertical motion and the net horizontal motion by applying some force at some angle theta. And I could figure out what that is. In other words, I know that all of the X components have to add to 0, and I know that all the Y components have to add to 0. So as long as I can figure out the X and Y component of each of these two vectors, well, now I just need to know that the X component of all three vectors has to add to 0. And the Y component of all three vectors has to add to 0.
Okay.
That's, to me, the essence of vectors, is when you're trying to figure out forces that... Vector problems can be kind of hard. There's a particularly hard vector problem that I can think of where there's a sine that hangs with a certain weight, and you have to build a bracket to hold that sine.
Huh.
And this weight might be 200 pounds. The sine weighs 200 pounds. Well, how strong does this part of the bracket have to be? It's a lot more than 200 pounds. That's a vector problem. In other words, we've got a vector going straight down. So this piece of metal right there has to be strong enough to withstand a vertical force of 200 pounds. Well, if we know that angle, then it's just a trig problem. And this would be 200, and let's say that angle is 60 degrees. Well, that would have to be 400. So the strength of that piece of metal has to be 400 pounds in order to hold up that 200-pound sine, because it's at an angle.
Yeah, okay.
Okay, but that's a vector problem.
Okay. Huh. Cool. Well, that's nice. That kind of gives me a context on like what they are.
Yeah, and as far as the brackets go on vectors, that just tells you that it's a vector. And it's giving you the X and Y coordinate of the vector. I think, I don't know, it's been a while since I've done vectors. Let's see, does that come before polar? Yeah, it does. Oh, you're talking about these brackets. You're talking about that.
Yeah, I think kind of, and then there's 4 numbers inside of them.
Yeah. In other words, I might define a vector this way. And what that's doing is defining the vector whose point is -3 plus 4. So that would define that vector right there.
Okay.
In other words, this is the end point, the coordinates, the X and Y coordinates on the vector.
Okay.
And if you're adding vectors, you just add individual components. If I'm adding that vector to another vector that's 5, 2, then the resultant vector is 2, 6.
Oh wow, that's kind of easy.
Yeah, it's very easy. the other way they talk about doing it is tip to tail, or draw a parallelogram and go straight across like that. When you're adding vectors. I don't know if I made myself clear there. Let's say we have a vector that is 4, 1, like that.
Yeah.
And we're adding another vector that goes to 2, 6. And what I want is that vector right there.
Okay.
I've done something wrong. I'm going to have to review my vector chapter. That's not right, what I just did. That is the resultant, but you don't get it by adding the numbers. I would have gotten 6, 7, and that's not where that point is. Yeah, let me, before I start dispensing knowledge about vectors, I may need to, here's the thing about vectors that might not be obvious. This vector is the same as that vector.
Why is that?
Well, because it's got the same magnitude and the same direction. That's what makes vectors equal.
Okay.
Okay? So any vector that has this direction and that same magnitude is going to be the same vector. In other words, if I draw another vector out there like that, that's the same vector. If I draw a vector like that, well, it's the same vector in the opposite direction.
Okay.
So my direction might be, instead of 30 degrees, it would be 210.
Yeah.
But vectors are the same if they have the same magnitude and the same direction, regardless of where they start and end. Because this vector is at the origin, doesn't matter. I could pretty much take all of these and make it the origin. So when you see a vector that has a coordinate of that, that means if one end was at the origin, the other end would be at 6, 2. But
Yeah.
it doesn't have to be like that. In other words, this point here could be 1, 1, which would make this point here 7, 3. In other words, the difference in the 2 points gives you the vector, despite the fact that it doesn't start at the origin. I would define this vector here in this manner. Left arrow 6, 2, right arrow. Despite the fact that it starts at 1, 1, not the origin. If it did start at the origin, this point would be at 6, 2.
Okay.
That's pretty much what they do. In other words, no matter where the vector starts, you can name it by just 2 coordinates, and that presumes that the beginning of the vector starts at the origin. So this vector right here that I drew, that would be defined that way. 6, 2.
Okay.
Okay, in other words, you always make one end of it at 0, 0, basically.
Okay.
Now, let me think for a second here. There's one in the book that they've got this vector here, which is u. That goes to -1, 3.
Okay.
And then they have another vector that's 3, 10. Okay, but I don't plot that at 3, 10. It's 3, 10 from there.
Oh.
And this point here would be, no, hold on, I'm not explaining this right. That's because that second vector wasn't 3, 10, it was 4. Yeah, okay, now, it was 4, 7.
Okay.
Now, if I want to know, yeah, that's not the coordinates of this point. That's the vector, 4, 7. In other words, if I was drawing that second vector from the origin, it would look just like that.
Okay. Yeah.
Okay. Now, if I want to add vector u to vector v, then I just add the x coordinates and I get 3, 10 and the y coordinates. And so what 3, 10 would be this vector right there, u plus v. In other words, when you add vectors, you add their individual components. In other words, 4 and -1 gives you 3. 7 and 3 gives you 10. And that would actually be the coordinates of that point, 3, 10.
Okay.
And it's called tip to tail. The reason is that's the tail of u. And so I'm putting, that's the tail of v. I'm starting it from the tip of u, going in the direction of the vector, 4, 7. In other words, I would go over 4 and up 7 from this point right here. And then that gives you the new coordinates of the resultant vector.
Okay.
Yeah, and a lot of vector problems are pretty easy. Adding vectors is easy. Multiplying by a scalar is easy. In other words, if I wanted to know what 3u is, that's -3, 9. Because u was -1, 3. So 3u is 3 times each of those.
Okay. Okay.
I will stop there with vectors, giving you a real basic vector education.
Yeah. Well, it's just something kind of nice to like see because I have these on my test.
Yeah, it is. If you gave me problems, you might give me some problems that I wouldn't be able to do. I don't know. It depends on how hard. You can make vector problems awful hard, put it that way. But I would just wait until you get some problems on vectors and then let's go over them.
Yeah, definitely.
All right. You got anything else tonight, Nick?
I don't really think so. Is there anything else you'd like to go over you think I should know for the polar graphs?
Just know that polar goes on top of XY coordinate system. It's not a separate coordinate system.
What does that mean?
Well, it means that whatever I can graph in the XY coordinate system, I can graph with polar.
Okay.
In other words, I can graph a circle, right? The equation of that's x squared plus y squared equals r squared.
Yeah.
But I can also, on the same XY coordinate system, I can graph that and by r equals 2. Same one. If I want the XY equation, it's this. But if I want the polar equation, it's that.
Okay.
Or x squared plus y squared equals r squared.
Yeah. Okay.
Again, I think it'd be better to have you give me problems regarding polar equations. Most of the problems they're going to give you are converting polar coordinates to XY coordinates and vice versa.
Yeah.
And the only thing you really have to know for that is that x equals r cosine of theta and y equals r sine theta. Those are your two main conversions. And also, sometimes you need this one, x squared plus y squared equals r squared.
Okay. And
generally, that one will convert most anything.
Okay. Well, am I going to start getting like equations that are like polar equations where I have to convert from back and forth?
Well, you might have to solve polar equations, yes.
Okay.
And a polar equation can come in all kinds of forms. Here, let me see if I can find one. Oh yeah, this is good stuff. This is where we get into vectors, parametric equations, and polar equations. These can definitely be challenging if you don't run into them very often. Let's take this. R equals 4 cosine of theta. If I want to convert that to an XY equation, it's an interesting solution. I multiply both sides by r. That gives me r squared there. 4r cosine of theta. Well, r cosine of theta is x. This is x squared plus y squared. So there's your rectilinear equation for that polar equation. In other words, the polar equation had r and theta in it, and my rectangular equation doesn't. Has just x and y in it.
Okay.
And then this actually, you can complete the square and do all kinds of things with this, but
okay.
Yeah, let's not get too much more into polar tonight. Just because, again, it would be better if you were giving me problems.
Yeah, and I think next class period I'll have some more definitive problems.
Yeah.
Over.
Let's wait until
then. Cool.
All right. Well, if you don't have any other questions, let's call it a session.
Okay, sounds good. Thank you very much, Mr. Cohen.
All right, Nicholas. Congratulations again. When are you headed out there?
Like, would you on a visit or on like
when do you go out there to go to school? Is it July or August or June?
Oh, I'm a junior, so it'll be
junior. Wow.
Yeah.
You accepted college already as a junior.
Yeah.
Wow,
So
I didn't know they did that.
Well, so what they did at Mercer is I sent all my scores, my test scores and everything, and for athletics, they can send it over to their admissions process and get what's called an academic read. Wow. And it's whether this kid will be accepted or not. And then if he is accepted, it'll be like his scholarship, what his scholarship would be, and stuff like that.
I gotcha.
So they can get a definitive answer when I do officially apply.
Well, that's pretty tremendous. You must be a great lacrosse player.
Thank you very much. Yeah.
Get a scholarship as a junior. That's pretty tremendous. Wow, I forgot you were a junior. I just assumed when your mom said you got a scholarship that you were a senior heading to school. But no, it
Yeah.
makes more sense. Yeah, I knew you were a junior. I just forgot.
No worries. Yeah, I'm really excited. I'm very excited.
Good. All
Hmm.
right. Well, Nicholas, I will talk to you next time.
Awesome. We'll talk to you next time. Thank you again, Mr. Cohen.
All right.